Hello everyone, my name is Umesh Silla and today I am excited to present my project Speech Emotion Recognition System which focus on the integration of signal processing principle with the deep learning techniques required for emotional insight. First one is project overview, the end-to-end SCRS pipeline. On this slide we see the complete end-to-end pipeline for our speech emotion recognition system or SCRS. The system is an integrated pipeline designed to classify human emotional states directly from speech signal. The entire process can be broken down into the three main stages. First one is audio processing and feature extraction. Raw audio undergoes processing and transformation into numerical feature vector using short time Fourier transform and mel frequency capturing the acoustic essence of emotional expression. Second one is deep learning classification. A convolution neural network architecture is employed robust pattern recognition trained on diverse dataset to establish sophisticated mapping from acoustic features to emotional categories. Third is real-time detection. The final result is system that can detect emotions in real time, classifying speech into one of eight categories: angry, calm, disgust, fearful, happy, neutral, sad, and surprised. We have achieved an accuracy of approximately 85% on our benchmark dataset. Dataset Foundation Revedes. This is high quality, professionally curated and balanced dataset which is essential for training a robust model. As you can see, it's very comprehensive. It contains over 7,356 high fidelity professional recordings. It features 24 professional actors, 12 male and 12 female, to ensure speaker diversity. And it covers to 8 emotions we target from neutral to surprised. Most importantly, Revedes has a structured file naming convention. This allows us to automatically extract the correct emotions label for every file, which is critical of our supervised learning workflow. EDA, the feature engineering process. Looking at the emotion distribution pie chart, we can see the data is well balanced across all 8 emotions. The gender distribution is perfectly balanced emotion by gender, so that we have recordings for nearly every emotions from both male and female actors. And the source distribution, so we are using both speech and song file which helps our model generalize. Signals and system, the foundation. Now let's talk about the chord theory. The entire project is fundamentally rooted in classical signal system theory. We must first understand how to treat speech as signal before we can extract emotion from it. There are three key concepts. First, the acoustic signal. We model speech as a non-stationary signal. This means its properties like frequency and amplitude change rapidly over time. These changes are what convey both the words we speak and the emotions behind them. Second, the transform domain. The Fourier transform converts time domain signal into frequency domain representations, revealing the spectral energy distribution across different pitches, key indicators from emotional expression. Third one is windowing and filtering. Short time Fourier transform applies window function to analyze small quasi-stationary signal segments, providing localized spectral content views essential for emotion detection. Key feature extraction techniques. Building on that theory, we move to feature extraction. Our goal is to transform the raw audio into compact numerical vector that our machine learning model can understand. We focus on two industry standard techniques. First one is male frequency capstral coefficient. As I just mentioned, this process generates spectrograms which are time frequency representations of the audio. You can think of them as images of the sound. Second one is short time Fourier transform. Short time Fourier transform segments the signal into smaller temporal frame and computes the Fourier transform for each segment. This process generates spectrograms in time frequency represent represent that visually capture dynamic spectral content evolution. Essential for analyzing non-stationary speech signal, provide time frequency resolution trade-off and found for generating male spectrogram. Visualizing acoustic feature. This slide perfectly illustrates what those features look like. In the first column, you see the raw waveform in the time domain. It's difficult to see a clear pattern. Second column, you see the spectrogram generated from the single single time Fourier transform. This is second 2D image where the x-axis is time and y-axis is frequency and the color is amplitude. Third one is see the male spectrogram. It's similar but the frequency axis is warped to the male scale which mimics human hearing. Zero crossing rate. This is simply the rate at which the signal crosses the zero amplitude axis. A high zero crossing rate or a lot of crossing indicates high frequency noise like in an angry or shouted voice. A low JCR indicates a smoother lower frequency signal like sad speech. And next is spectral centroid. The spectral centroid represents the central of mass of the frequency spectral, providing insight into the perceived brightness or sharpness of a sound signal. This is the center of mass of the spectrum. It tells us where the energy is balanced. A high centroid value means a brighter sound like a happy or angry tones, while a low value means a duller sound. Common is a shared expressions. Next one is third spectral bandwidth. This measures the spread of the energy around that centroid. A wide bandwidth means a complex noisy sound, and while a narrow bandwidth is more pure tonal sound. Together the centroid's bandwidth gives a powerful description of the spectral shape. Spectral roll-up, quantifying sound brightness. This feature finds the frequency below which 85% of the spectral energy is concentrated. High roll-off frequency means a brighter sound with a lot of high frequency energy, while a low roll-off frequency means a duller sound. Male frequency spectral coefficient. First First apply a Fourier transform, then use male filter banks to scale the frequencies based on human perception. Third one is we take the log to mimic how we perceive loudness. And finally we apply a discrete cosine transform to decolorate the feature, making them highly efficient for machine learning. फिर आता है डेल्टा कैप्चरिंग इम्पोरल dynamics. Delta means change. The delta are the first order derivative of the MFCCS, meaning by the capture the rate of the change of the feature over time. This is crucial because it captures the temporal dynamics of the speech, not just a static snapshot. Traditional audio feature, a comprehensive overview. This slide provides a quick summary of all the traditional features we just discussed, from the ZCR and spectral centroid to the MFCCS. It categorizes them by their domain, whether they are time domain, frequency domain, and capstral features. This combined set of features bridge up the gap and between signal processing theory and machine learning practice, giving our model a rich, comprehensive view of the audio. Convolution neural network for audio. With our feature prepared a 2D spectrogram, we can now build a for classifier. The first component is convolution neural network (CNN). CNN are perfect for this task because they are designed to find forensical spatial features in this image by treating our spectrograms as image. The CNN can learn to identify complex patterns across both time and frequency. The convolution layers act like detectors, finding local patterns like specific tones, harmonics, or sharp change in the audio. The pooling operations reduce dimensionality and provide translation invariance, making models robust to slight shifts in time or frequency. LSTM networks modeling temporal dependencies. But speech is not just static image; it's a sequence that unfold over time. This emotion in a word can depend on the words that came before it. To handle this, we add a long short-term memory network or LSTM. LSTM are crucial for modeling these long-range temporal dependencies. They are ideal for recognizing patterns that unfold over time, like prosody and intonation in speech. They are internal gates and input forget output gate to control the flow of information. This allow to network and to selectivity and remember important context from early in the audio and forget what the not relevant. CNN architecture for spectrogram classification. This slide shows the specific architecture we implement combine the two models we have just discussed. We start with a stack of 2D convolution and max pooling layer. These process the input melt spectrogram, extracting the spatial features. The output of the CNN block is then flattened and the fed is into our LSTM layer, which analyze the sequence. Finally, the LSTM output goes through a series of a fully connected layer, which perform the final classification, ending a softmax layer that output the probability of each of the 8 emotions. Monitoring convergence. This slide shows the result of the OR model training. Monitoring these curves is critical for Darnagage performance. As you can see, both the blue training and orange loss curves decrease steadily, which indicate the model is successfully learning. Crucially, the validation loss tracks very closely with the training loss. This is excellent. It demonstrate that our model is generalized where the unseen data is not memorizing the training set. If we saw a widening gap, that would signal or overfitting, but our results show a robust and well generalized model. Comparative performance analysis. So to summarize our findings or analysis so that the selecting the optimal architecture this combine or CNN LSTM is critical for a high performing audio classification task. But the project does not end at this. SCRS pipeline has broad real world implications across many fields. In customer service, it could monitor calls in real time to detect customer frustration in mental health. So it could be a screening tool to detect early sign of depression and anxiety from a person voice. And in driver safety, it could detect fatigue and stress in a operator voice to prevent accident. Thank you.